Okay, it's 9 o'clock. I guess there are only 2 people here. I'm hoping that others will show up or here or online. I'm impressed with the PI guys. You guys show up 3 out of 4 is not a bad number. I just wanted to remind everybody that they start the that this is the last week of class, and the presentations for the LSU guys are scheduled on May 5th, which would be the Sunday, end of this week. And we will start at 9 o'clock, but I will revise the schedule so that the PI people will be rescheduled for a later date, because your term doesn't end. Our term ends, classes end of this week, and the exam starts next week. So the presentations are to be done this coming Sunday from 9 o'clock in this room. And the report is due by Friday, I think I said 4 o'clock, this Friday. Okay. And then the oral exam will be scheduled again next Saturday from 9 o'clock. For the presentation, all of you must be present here. Only the LSU guys, PI guys, if you want, you can show up. We will put it on the internet, and I will also record the presentations, not using Camtasia, which requires a lot of conversion and stuff, but we will try that. Adobe has a recording feature also.
Yeah. So we have to submit the presentation on Friday before.
You have to submit your report.
But I thought that was for next Friday. Am I right? Next week. Next week.
Is it?
Yeah.
Oh, next.
Yes.
10. Okay. Oh. I'm sorry, I stand corrected.
I just wanted to.
I sent you a shock mail. Okay, the reports are due next Friday, because the exam is scheduled Saturday, 11. So the reports are due by 10, Friday, 4 o'clock on Moodle. So just upload it on Moodle. And so the presentation then is going to be just nothing to be submitted. Okay, just listen to you, and then we will use the Adobe's built-in recording feature to record your presentation, so that you can listen to it, and it's a learning opportunity. If you listen to yourself talking, there is some important feedback that you get from it. Okay, and so this is just a reminder of what is coming up. So for the PI guys, I will email you to fix up. I think we were talking about middle of May, but we just you need to tell me when I need to submit the report, the grades to your institution, and we need to wrap this up before that time. Okay. Any questions for me on these? Okay, if there are no questions, I think Santiago had a question by email, right? Do you want to post that question again?
Yes. In my problem, I got a time-dependent boundary condition. So I wanted to know if I should call that boundary condition non-autonomous boundary condition, or it is okay to call that boundary condition non-autonomous boundary condition. That's my question.
Yeah, I think that's a very good question. So I kind of gave you a very terse answer by email, but I thought I should take some time to pose the question. These are the kind of questions that I have a list that I'm developing, right? So it allows you to connect what we have seen and I guess see how well you can respond to this question. So let me repeat the question. So if you have, I'm just going to make up a problem, okay? If you have an ordinary differential equation like this, dc dt equals alpha d squared t dz squared. That's a parabolic partial differential equation. and let's subject that to a set of boundary and initial conditions. So the initial condition is going to be t for all x at time equal to 0 is some function of x. Let's say it is sine 2x, something like this. Okay? And then it's a second order in z. So sorry, it should be z. So I must need two boundary conditions. So boundary condition 1 is t at z equal to 0 for all time is varying as sine 5. Okay, and then the boundary condition 2 is t at z goes to infinity or a large number for all time is some number 10. Okay. So the question that Santiago asked is, when I solve this problem in console or in the software, if I have to ask you to classify this, of course the first classification would be in the partial differential equation, is it parabolic, elliptic, or hyperbolic, and it turns out to be a parabolic equation. And you, for example, use the method of lines, just to make you, give you a concrete example. Okay? So this is z. Z goes from 0 to a large number, infinity here maybe. Imagine that this is a problem actually for transient convection. Okay? Suppose the Earth's surface is undergoing a periodic change in temperature with time. Okay? That is between summer and winter, for example. Okay? And you want to answer the question, this is a problem I guess coming from people in the north, cold climate. You need to design how deep should you bury your pipelines, whether it is water pipeline or whatever it is, so that it doesn't freeze. Okay? So you need to know what is the depth to which the temperature can go down to 0. Okay, if you know the depth and if you bury it below that, it will never reach 0 in that part and you are okay. So in such a case, you have the surface temperature changing in a periodic fashion with time. Now this 5 may not be maybe some other number depending on the period of the oscillation, depends on what time I am using as well. Okay? So in such a case, when I take this and discretize the spatial variable, that's basically the approach. Okay? We discretize the spatial variable and sometimes we discretize the time variable also. Others will say just an ordinary differential equation that I will use any ODE integrator, because we've seen algorithms for integrating ordinary differential equations. That is the method of lines. Now, you can apply that to finite difference approximation, you can apply that to finite element or finite volume. Its ideas are the same. So when you do that, what you're going to do is you're going to convert this into a system of ordinary differential equations. Now T is a vector containing the values of temperature at the nodal points, whether it's finite difference or finite element. Okay? So you're converting the PDE into an ODE and then you know how to integrate. The question now is that an autonomous or a non-autonomous system? First question you try to answer would be, will time appear explicitly in this function? What do you think? For this problem, when I do the discretization, do you understand how you would take this and get all these functions that you need? Whether it is finite difference or finite element? In the case of finite difference, it's easy, right? All I have to do is construct a mesh and replace that by central difference approximation. You're going to get a set of vectors. But when you apply the boundary condition at the edges, okay, so at t equals 0 along this line, the function is changing according to this, right? So that function will have a dependence on t, because the boundary condition will enforce a variation in time continuously. Okay? So such problems will not have a steady state. By nature, I'm forcing it with a periodic excitation from the boundary, so the response must be, the long-term response must be periodic. And we have seen how to solve these kinds of problems in the transport phenomenon. Of course, when you're forcing it with a sinusoidal form, there's separation of variables in this particular case, a linear problem. And not only separation of variables, but you can, when you're separating it, you can say the spatial solution must consist of only sines and cosines because it's a periodic excitation, so the response must also be periodic. But when you get numerically, if it is nonlinear, this can still be done. And what you would call that would be a non-autonomous system. Okay, so when there is excitation from any other, so this is, it can be extended to two spatial dimensions. Okay? If there is excitation from the boundary data that changes with time in these evolutionary problems, both parabolic and hyperbolic, then you will end up with a set of ordinary differential equation. In the case of a hyperbolic problem, you won't follow this method. You will follow the method of characteristics, which we have not done in this course. And of course, we know what how the classification of partial differential equation goes. So in the case of a parabolic problem, you have a degenerate characteristic line. So you can think of these as the characteristic lines along which information propagates, but it diffuses also as the information propagates along each one of these lines. In the case of a hyperbolic equation, you have these characteristics that are real. Okay, so you can actually construct what these characteristic lines are, and information is carried along those lines without dissipation. There is no dissipation mechanism, and so you can construct the solution knowing what the initial condition is. So if you know that which way the characteristics go, that information is carried along the characteristic line. Okay. But I'm not going to hold you responsible for hyperbolic equations in this course. Parabolic and elliptic equations, yeah, you should be able to think through. So, does that question? Okay, so it's an extension of what we have talked. We have not explicitly talked about this, but you should be aware of such extensions. Okay, any other questions? Okay. So if there are questions, put them on the chat box. I will try to check periodically. I should get better at it. I have not been doing that properly. Okay, so the last topic I want to cover is the so-called finite volume method. What is the mystery behind it? How do we convert a partial differential equation into a set of ordinary differential equations or algebraic equations? How do we do the spatial discretization? So these three methods have distinct characteristics, but they all try to do the same thing. Take a differential equation, do the spatial discretization to get an algebraic equation or an ordinary differential equation in time. Okay. So in the last lecture we saw how the finite element method does. Of all the three methods, probably the easiest to understand is finite difference. Because if you give me a table of derivative approximations and throw any differential equation at me, I can always replace it by a set of difference approximations. But the problem is, what is the problem with finite difference method? What are the challenges? The grid spacing must be uniform, and so for complex geometries, it is very difficult to fit unless you do a mapping of the grid from one domain to another domain. And such things exist, but still this is to be done for each geometry, each problem. So it is not as popular in commercial softwares as finite element or finite volume. Both of them approach the problem from the beginning in a way that removes of that constraint, so that I can construct any mesh and I can set up the problem. But the key idea in the finite element method is method of weighted residuals. That's the starting point. Okay? So it's in some sense an abstract approach. So you give me a differential equation, I find the residual, left hand side minus right hand side. Residual is not equal to 0. I find a weighted residual integral of. So I convert a differential problem into an integral problem by defining this weighted residual. And then I say I'm going to satisfy this residual, minimize it, or set it equal to 0 in certain subdomain. So that gave rise to a whole class of problems. So that is the key idea on which the finite element rests. Okay? And particularly in the finite element method, we have a weak variational form. You should understand what the weak variational form is. We do integration by parts. When you go from the differential to the integral representation, it is purely a mathematical exercise. The reason I'm emphasizing that is you will see in finite volume method, It's a physical argument that takes us from the differential to integral world. Both of them follow essentially the same approach. But we don't talk about residuals, we don't talk about weak variational form or anything, we talk about conservation laws. How do I enforce the conservation laws in arbitrary shaped controlled volume? Okay, so it looks like then it must have no error. Okay, but there are reasons why there are errors, and we need to understand that. So in the finite element method, you need to understand what are the basis functions of the test functions, and the Galerkin method in particular, where the weighting function is chosen to be the test functions. And the other important part is the concept of a local support for the basis function. If your basis functions can span the entire domain, which puts again restrictions in terms of the complexity of the boundary. Okay? But if you have a local support, meaning one function spans only 3 grid points, for example, just like we did in finite difference method, one derivative approximation spans 3 points. This you can do with over 4 points or 5 points, so that will determine the structure of the matrix that you eventually get. But such approximations have essentially large sparse matrices. Okay? And instead of a linear, you can pick a quadratic or a cubic, etc., as your basis functions. But they have some nice properties. The nice properties are at x1, for example, the function p1 will be 1. Okay? And at 0 and 2 will be 0. And so you can directly, unlike in the method of weighted residuals, where you're solving for coefficients of the expansion of the solution, here you get directly the unknowns of the nodal points, the feature that we liked in the finite difference method. So we get the same thing. But you need to work through this basis functions, put them in the residuals, and carry out the integration by parts, and evaluate these functions to reduce it into a set of algebraic equations. Okay, so those are the key points in the finite element method. The details are enormous as you expand, particularly from 1 dimension to 2 dimension to 3 dimension. The bookkeeping, the coding, all get tremendous. So if you do, for example, a coding for even a 1-dimensional finite element method, I think you will learn a lot more than by just listening to me. But time constraint is there, right? So at least you get an idea of what those methods are. So the finite volume method, as I said, relies on physical concepts. So there are some excellent books in this. One is by Patenker, S.V. Patenker. It's called Heat and Mass Transport. So the method itself is developed for the convective equation as it originates. Okay, so you will talk about fluxes, you will talk about balancing fluxes. So the physical interpretation is very closely tied in the historical development of the finite volume method. Of course, it has been abstracted into mathematical process whereby you can apply it to other differential equations also. Whereas finite element had its origin in solid mechanics and follows a strictly abstract mathematical approach. So you can apply that technique to any partial differential equation. So it's a very natural fit for COMSOL. So COMSOL is based on, you can think of it as a finite element discretization. So if you look at this equation, it is a scalar equation. I have only one unknown t. Now all the equations in transport phenomena follow this template. Okay? So instead of t, I can replace it by c. Then I have convective mass transfer. T stands for convective heat transfer. But if I replace this by rho u, what do I have? I have momentum transfer, right? So in general, you will find that in this method, they will actually replace this by phi. And if you write a template of discretization process for that equation, you can apply it to any equation that has that particular structure. Okay? That includes the momentum equation, heat equation, mass equation, turbulent kinetic energy equation, viscous dissipation equation, and you can have any number of scalar equations. This is how Fluent, COMSOL, they generalize that. They just have a template for discretizing one such equation. If you understand that, you can apply it to any problem. Now, if you apply it to a momentum problem, what will be the interpretation for phi? As I said, it will be rho u. That makes the problem nonlinear. But if phi is anything other than the momentum, like temperature, it is a linear problem. But you have to assume that u is a known quantity. Where does it come from? From the momentum equation. So you need to solve the momentum equation And in the energy equation, you assume that it is a known quantity. And the only unknown is the temperature. So alpha is the diffusivity. Okay? So that U must satisfy the, for incompressible flow, must satisfy the continuity equation. Okay? So U cannot be arbitrary. It is a known function. It is a, as far as this equation is concerned, but it is not any arbitrarily specified function. It must satisfy the continuity equation or the mass balance equation. Okay? So you can write this equation in a slightly different form called the conservative form. This one is called the advective form. So it's a common terminology that is used that you must understand what we mean by that. So an advective form simply says that the quantity that you are dealing with is advective, meaning it's moved with a certain velocity in the direction of the velocity field. Okay? So it could be concentration or it could be temperature, but it is advected with that. It's like a Lagrangian description. In fact, we have seen the left-hand side as a called a substantial derivative or total derivative, the transport phenomenon, of course. Derivative following the motion of a particular fluid element, right? So that is why it's called an advective form. But if you combine these two equations, you will get a conservative form, which looks like this. Same equation, but this is called a conservation form. So what did we do? How did we achieve this? It's very simple. Okay, you take this expression, del dotted on U and T, and apply chain rule on that. Do it in index notation, expand this in index notation, and it's this exercise I think you have done in the fluids course. And when you do that, you will get U dot del T. Okay, so that is, you take the U out first, operate delta on T. So you will put the dot between U and delta because both are vectors. T is a scalar quantity. Plus, the chain rule requires you to keep the other one constant, right? So you take that T out, but then make sure that you put the delta dot between delta and U. Okay? So this is essentially chain rule going this way. Chain rule expansion going this way will give you that. Okay? But you know that del dot U is 0 by continuity equation. So that interpretation that U there is a velocity field satisfying continuity equation for the incompressible Navier-Stokes equation. Okay? So this form is called the conservative form. Now, why is it called the conservative form? What is the interpretation for this? What can you call that term U times T? Probably you should see it as, here alpha is written as the thermal diffusivity. So alpha is K divided by rho Cp. Okay? So K is the thermal conductivity, but rho Cp is hidden in that alpha. So if you expand this and bring it back and multiply every term by rho Cpt, here rho Cpt multiplied by U. Okay? What would you call that term? That is the flux. Like if you look at the units for that, it will be so many joules per second meter square or watts per meter square. Okay, so it's a flux, but it is a convective flux. It's a convective flux because it is being convected with a velocity u. Whereas this one is, what is this one? A diffusive flux, right? By convection, by mass diffusion. Instead of T, you have C. So you can put both of them in the same operator if you want. Del dot combined flux, the total flux, it includes the convective flux and the diffusive flux. So that would be our starting point for the finite volume method. You express it in conservative form, and you take an arbitrary control volume. Okay, so that's the thing that you see here. With an arbitrary control surface, it need not be spherical. In this particular case, they've drawn it as a spherical one, but it has a normal to the surface and a velocity vector pointing out. This is not a material volume. It is not a Lagrangian description. It is a volume fixed in space. So you could have material that enters this through a velocity field and material that leaves it through a velocity field. Okay, so when a material enters with it, it brings in its momentum, its mass, its energy, whatever. And when it leaves, it takes away. So the difference between the what comes in and what goes out is equal to your accumulation of material within the control volume. Okay? This is how we go from the differential to the integral representation. So in fact, if you remember, those who have done the transport phenomena course, this is how we derived this equation. We formulated the equation in a Lagrangian frame, and then using the Reynolds transport theorem, we converted that into a differential form of the equation. So we are now going to go back and get into the integral domain, but in Eulerian reference frame, not on a Lagrangian. What would it be in Lagrangian reference frame? What would be the velocity? Can there be a velocity entering the control volume? No. Why? Because Lagrangian means that you identified certain material particles in there, and they are not allowed to leave or enter. Okay, you're going to track their fate forever. That's a Lagrangian description. And ALE tries to combine both the viewpoints, the Eulerian and the Lagrangian viewpoint, where you allow your mesh to move, so the mesh will have a certain velocity. But in this Eulerian form, the mesh is going to be fixed. So you could have a triangular domain like that, and each one could be a control volume. And in which case, all you need to do is enforce this equation at the control surfaces, where you have the normal. So you need to track how much of material comes in through each one of these surfaces. Okay? So you are treating it in a conservative form, and you're looking at the fluxes that are coming in and leaving in an arbitrarily shaped but fixed control volume. That's a key to understand finite volume methods. Any questions on that? Okay. So here is the integral representation. So what have I done? I've taken that equation that you see here and integrated it over that control volume every term. Okay, over. So it's valid of course at every point, but now I'm saying it's valid on a scale that's much coarser than the continuum scale, on a grid scale. So I construct a grid and I integrate that over those grid points. So the delta V is my arbitrary but finite control volume. So that equation is essentially putting the integral in front, but what is the next part? I have switched the derivative and the integral. When can I do that? The mesh is not moving. Okay, it's a fixed Eulerian reference frame, and the functions are continuous. So whether I take the derivative and integrate it afterwards, they are linear operators, they are switchable. So I'll get the same result. I can give this a new meaning. What would be that meaning? That would be the average temperature on the cell. So the rate of change of the average temperature on the cell. And if you multiply it by rho Cp, you can interpret it as the rate of change of energy inside that cell. Okay, the rate of change of energy inside that cell equals the flux coming in and leaving around the surface, delta S. Okay. Now, what did I do in going from here to here? I used divergence theorem. Okay, so that's a strict rigorous result. I've not lost, I've not made any approximation. Okay, so I've just used to convert a volume integral into a surface integral. So del dot something is the same as n dot something integrated over the surface. Okay, so in both places I've done the same thing. So there is no approximation. Okay, in going from 17.4 to 17.5. But what I need to do is, I need to know where the normal is on the surface of my control volume, whether it is 1D, 2D, or 3D. And then I need to be able to evaluate these fluxes and integrate them. Okay. So now I've gotten into an integral formulation, just like I did in finite element method, but without referring to weak variation form or anything like that. But keeping in mind that I'm giving it always a physical interpretation, that it is that net fluxes across the interface is equal to the rate of change. Here I have made one assumption. That assumption is that there is no source or sink inside my control volume. So if there is a reaction, for example, that is taking place in a reactor, okay, then the concentration will change because the reactants are consumed or the products are produced. And the energy balance, you will have a source of heat of reaction. Okay? So sometimes, of course, it must always be generalized in COMSOL and other places. So you will have a Q term, a source term. The source term must also be integrated. So you should know what is the total source or sink of heat or mass or whatever it is over the control volume. But this development is ignoring the source or sink. So as I said, a few key points that we are assuming that this is fixed in space. That's what allows us to switch the derivative and the integral. We have used the divergence theorem to change the volume integrals to the surface integrals. Okay? And we can give it a physical interpretation as we talked about. Okay? And this is a limiting case. Suppose there is that this control volume has an insulation boundary condition. So there is no flux of heat conducted into the material, and it's a solid, so there is no material entering or leaving. Okay, then this will be 0. That means such a material must remain at a constant temperature forever, unless you have a heat source. Then you can have, again, a coordinated differential equation. So our focus is going to be to construct spatial discretization. Okay, so the time is simply treated as a time integration marching in time, using all the concepts that we have seen before: explicit discretization, Euler formula, or modified Euler formula, implicit discretization, or even higher order discretizations are possible. Okay, but it's a spatial discretization that we are focusing on. And the other one is that delta V and delta S are arbitrary. Okay, so there's no specific size or shape. That gives us flexibility to fit this into any complicated shape and put variable size control volumes. If things are changing very rapidly, you want to put smaller control volumes. If things are not changing, you can just take a larger control volume. So where would you think the source of error be? In what we have done so far, I've said there is no source of error except for the assumptions that I make in the model itself. If I say there is no heat source, that's an assumption. I can come and rectify that. So in terms of converting my differential equation, conservation equation, this template will work for momentum, heat, mass, turbulent quantities, etc. I have not made any assumption, right? And I could relate, if I put a mesh and carry out this integrals, I could relate the quantities at one cell to the neighboring cell, because I can track how much of material is leaving one cell that must enter the cell through the common surface between them, right? So I can assemble all these equations, and it looks like there is no truncation error, there is no error, but where do you think the error will come from? We need to evaluate the fluxes, diffusive fluxes, delta T. How do I evaluate delta T? I need to know the gradient. Okay, so one way of doing that would be to construct our mesh in such a way, and this is one of the key distinguishing features of finite volume method, and the number of books that have appeared, they will all follow the same terminology that Patenkar laid out. Patenkar and Spalding, I think, were some of the original developers of these ideas. So everybody follows the same nomenclature. And I will reveal that, I guess, in the next look at the mesh. Yeah, here it is. Okay, so this is a sketch for a general three-dimensional geometry. So it's your fixed control volume. It need not be a cube. It could be any arbitrary shape. But if it is a cube, then what you will notice is that on the x-axis, you have an east face and a west face. So that face is the east face, and this face is the west face. Okay, east-west on the x-axis. And on the y-axis, okay, you will have north and south. Okay. So north on the face that is behind, and south on the face that is spacing is. So we need to evaluate the fluxes, the diffusive flux and the convective flux on all these surfaces, control surfaces. Okay, so you have the same thing on the other side. And then top down, you just use T and B. T for top. Okay. I'm not sure it's going to be crowded. Try that. Okay, so that is the top, and this is the bottom, this end. Okay, that's in this direction. Using that, carefully evaluating all the fluxes, the convective and diffusive fluxes, you reduce that differential equation to simple algebraic equations. Okay, so that's the essential idea, and we'll see how it is done for a one-dimensional case first. Okay, any questions? So delta x, delta y, delta z can change from cell to cell. Okay, so you need to keep track of what is the spacing, what is the size. So all those quantities you need to keep track of in a vector. Okay, the mesh-related information. You need to do the same thing with finite element method also. So the storage requirements for both the methods will be large because you need to know what the topology of the mesh is and what are the sizes in each of the three directions, etc. Whereas in finite difference method, you assume that they are uniform, so the memory load is not as high. These days, memory is not a problem, right? So you can easily solve in finite element or finite volume more large meshes. I guess we call the course as computational transport phenomena. This is what brings the whole thing that we have seen. What is this? These are the transport equations. Okay? So you have expressed in the form of conservative form. Okay, so here is the x momentum equation, rho u, and one of the u is a vector. That is the advective part of the thing. The other one is a lowercase u, the scalar. Okay, so this is what decides that this is the x component. Okay, so it is u, and this is the momentum source in the x direction. And if you go to the next one, it is v that you will see here. But this u is the attraction term or the convection term. That's a vector. Okay, so this quantity, momentum in the x direction, can be convected in the x, y, or z direction. Okay, so if you remember from transport phenomena course, it is a tensor. It's a dyadic product. If you have to write this in these three equations in one compact form, you'll have to write it as rho u dt plus del dot rho u u. Okay, and that is a dyadic product. Okay, when you decompose that into three components, then you get this u, v, and w component. And internal energy, okay, where I is the internal energy, which you can relate to through an equation of state to density and temperature, or pressure and temperature, etc. Okay. So those are the transport equations. I mean, you've seen all the elements of how to deal with those transport equations, except for one, and that is when you have an incompressible Navier-Stokes equation where this term is 0, this one reduces to just del dot u equal to 0. Okay, so that there is a special coupling mechanism that we need to impose because we have four unknowns, pressure and three velocity components. They are coupled. Okay, so these are coupled, but the other equations need not be coupled depending on what problem we're dealing with. If you have natural convection, it will be coupled. If you have forced convection, then the velocity field forces what happens to the temperature field or concentration field, etc. So four equations in four unknowns, but three of them are differential equations, but one is an algebraic equation, continuity equation for incompressible Navier-Stokes. So Patenker and Spalding proposed one way of handling that coupling, but I don't think we're going to have time to get into this in this course. Okay, so we're just going to see how the discretization is done for such transport equations in the finite volume context. So here is the terminology directly from Patenker's book. Okay, so the equation is written as rho phi and phi and s of phi. Okay, so phi is some scalar quantity that you are interested in solving for. It is being accumulated according to this term, advected according to this term, diffused according to this term, produced according to this term. So it's a transport equation where this term is kind of unique only to the transport processes. Okay. So a physical interpretation of that is rate of increase of phi, whatever that phi is. It could be energy, it could be mass, species, concentration, etc. So the net rate of phi out of the finite element, that is the integral over the entire control surface, and the rate of increase due to diffusion. Okay, one appears on the left side, the other one appears on the right side. That's why you see the change in word, net rate of flow out. Okay, whereas this one is net rate of diffusion in. How much does the diffusion mechanism deposit into the control volume? And the rate of increase due to sources. When we start developing these conservation equations, this is our first statement in plain English, and then we'll say, okay, let's try to develop symbolically what that equation is represented as. So we will go from here to this part. But in this book, what they're saying is, this is the equation, what is the physical interpretation? To give you a flavor that the method is rooted in the physical interpretation and understanding of the integration over the control volume. So it's exactly the same thing that we did, but in the general transport equation for any quantity phi. So we do the integration over the control volume. Okay, and we have the divergence which is converted into through the Gauss divergence theorem into a surface integral. Okay, so that is basically what the Gauss divergence theorem is. Okay, n dot a, where a could be any quantity. Okay, in our case a is this, or a is that. Okay, and what you will get out of that is this form of the equation. So once again, we have switched the derivative and the integral. Okay, and we have used the Gauss divergence theorem to convert the volume integral into surface integrals. And this is still an integration over the control volume, because that's a volumetric source of momentum or heat or mass. It's the same thing. But now he's saying I'm going to develop only for a steady state version of the problem. I'm going to focus on spatial discretization, because time discretization, I just use the standard methods for explicit and implicit method. Okay, so yeah, it's for steady state problems. Okay, so you drop the time dependent term and you just get these terms. As I said, there is no approximation in this other than model driven approximations like it is steady state or there is no source or whatever. But here, handling of the source term is important. There's something called source term linearization that you will see in Fluent, for example. So why is it important? How is it done here? You will see. Okay. So the problem, the challenging thing to deal with is this gradient term, to approximate that gradient. Yeah, he's just saying that in time-dependent problem it's necessary to do this, but we already know how to handle explicitly or implicitly. Okay, so let's not focus on that. Just go to the. This is all taken from the two sources. One is a book by Malasekara on finite volume method. The other one is Patenkar. Okay. So I thought this is important to reinforce. We have already talked about this idea. But when I was going through this book, I thought I should use that to reinforce two distinct type of problems. One is the equilibrium problem, the other one is the marching problem. Okay? The marching problems are typically time-dependent problems, parabolic or hyperbolic equations. In the case of a parabolic equation, the marching is in time. In the case of a hyperbolic equation, marching is in terms of along the characteristics for the particular problem, which you can easily find. But the equilibrium problems are ones that are elliptic problems, so there is no time dependence. But you will find that when you have a problem like the one that we just started off today, that is this one, okay? We said that this is classified as elliptic, parabolic problem, right? Because it is a marching problem, the temperature varies with time. But in these books, and I think it kind of appealing to me also, they make a finer distinction that they will still call this term, the equation is elliptic according to the definition that we have agreed on for parabolic or partial differential equation classification. But that term has the effect of propagating the information from both the boundaries into the entire domain. Okay? So they will call that as an elliptic type of equation. And this one would be called the parabolic type of propagating equation. Why is that distinction important? It is important when we consider this problem, which we did in transport phenomena course, okay? The Prandtl boundary layer theory. So you have a plate, okay, and you have fluid approaching with uniform velocity. I don't know whether you remember the equations that Prandtl derived from the Navier-Stokes equation using very careful scaling arguments, arguing that within this thin boundary layer, the viscous effects are important and the velocity gradients are sharp, but outside of that boundary layer, there is no velocity gradient. So potential flow is a good approximation. Okay? And we call this distance as the boundary layer thickness, and that depends on the distance x. So we call this x and y. And the equation, well, let me just remind you, what I'm trying to illustrate here is the difference between equilibrium problems and evolutionary problems. And typically we saw that evolution in time is fairly obvious in parabolic and hyperbolic equations. But you can also have evolution in space. So the problem looks like a parabolic problem in one of the spatial dimensions. And this problem illustrates that. So when you're developing methods, you should adopt a method that is meant for parabolic problem when you're solving the boundary layer equation, for example. Okay. So what are the boundary layer equations? If the velocity field is u and v, and they are functions of x and y, two-dimensional boundary layer theory. Okay. So the equation would be du dx plus dv dy equal to 0, the continuity equation. Okay. And those are all first order equations. And strictly, you cannot classify this as either as being parabolic or elliptic or hyperbolic using our definition, because this is a nonlinear problem. So when you write the x momentum equation, you'll get u du dx. So there it is. The coefficient is an unknown. U is an unknown, right? Plus v times du dy. Does anybody remember what goes on the right hand side? For a flat plate, Prandtl equation. Plus is solution, it's going to be d squared u d. That is the key part. You cannot forget what you learned. Think of physical interpretation of what the boundary layer is. The boundary layer is saying that it is whatever that is coming in, a disturbance that is advected in the x direction. So this is the entire advection of the x momentum equation in the x direction. Okay, and there is some part of it that can be advected in the y direction also of the x momentum. Okay, but what is this one? This should be the diffusion of momentum. So is diffusion, if I put x squared, what would it mean? It would mean diffusion of momentum in the x direction. So which is going to be stronger? This is the argument precisely that Prandtl made. Okay, when I'm comparing advection in the x direction, where I have a very large velocity forcing the fluid, or I am comparing that with molecular processes that diffuse the momentum in the x direction, which one is going to be larger? The advection term is going to be larger. Okay, so he basically argued that I can delete this. Okay, oops. Okay, now to imagine that it is deleted. Let me try again. Then It's not the problem with the smart board, it's the problem with okay, I'm not able to delete that. PDF annotator is having a problem. It should actually be y squared. That says that the diffusion in the transverse direction is important. You cannot neglect that. Okay? If you neglect that, what happens? The equation becomes the term that we have seen in transfer force, Euler equation. Right? That's basically you're saying that the viscosity is 0. The viscous momentum effects are 0, then it becomes the Euler equation. Okay? So that is the Prandtl-Bourgeois equation, which balances very carefully diffusion of momentum in the y direction with convection of momentum in both x and y direction. Okay? The other momentum equation in the y direction becomes trivial. Okay? That is, this will simply be dp dy equal to 0. That is, there is no pressure gradient inside the boundary layer. The reason I'm talking about this is, how would you classify this? Given that strictly we cannot classify this because these coefficients are all nonlinear terms. Okay? But the principal effect of this model is that it has only first derivative in the x direction, second derivative in the y direction that you see here. So it behaves like an elliptic equation in the y direction. This terminology you will see often used. Okay? So if you have second derivative, meaning that you need two boundary conditions, and those boundaries will influence the flow in the entire domain along that direction. Okay? Whereas in the parabolic direction, if I put a disturbance in this, at this point, I have a small perturbation there on the plate. Okay? Will I know about the perturbation here ahead of time? The answer is no, because the convection is so large, the information is carried from here, but we will see the bump, and its effect will be felt downstream. It has the ability to carry that downstream, okay? But it doesn't have the ability to carry it backwards. What mechanism do you need for it to be able to carry it in the backward direction? You need momentum diffusion in the x direction. So if you put the term d square u dx squared, that will tell you that there is a perturbation there slightly ahead of time. But still it depends on comparison with u and that viscosity term. So if u is dominant, you will see maybe a few nodes before that feeling that effect of the particular disturbance. Okay? So this would be called a marching problem in the x direction. It's parabolic in the x direction, but elliptic in the y direction. Okay? So you need to devise a method that will take care of this nature. That means, what does that mean? When you're using finite difference or finite element, you will have basically a given information here that will affect what happens in the next level, what happens at the next level, but you don't have the ability to do it propagate it backwards. So it becomes like a time marching scheme, but except it's in a spatial dimension. Okay? So there is a whole number of problems that are based on this idea of what they would call parabolized Navier-Stokes equation. So we take the Navier-Stokes equation, but parabolize it in one of the dimensions where advection is very strong. Okay, so you don't worry about diffusion in that direction, and then solve the problem. So is that idea clear? Okay. So if you go back to what those guys doing. Okay. So the equilibrium problem versus marching problem, you should interpret it carefully. Thank you. You heard me. You're paying attention. I'm really glad. Somebody is paying attention. We are able to see the pop-up today. Sometimes I don't pay attention to it. Thank you, Rishi. So we are trying to understand what is the difference between an equilibrium problem and a marching problem. The marching can be not necessarily with respect to time. It could also be with respect to space. Okay? But it essentially tells something about the ability of information to be propagated in both directions versus only in one direction. So marching problem will have that feature, that you will be propagating the information only in one marching direction. And elliptic problems in 2 dimensions, 3 dimensions, they are well behaved in that sense, because whatever you put on the boundary is going to influence the entire domain. So if the boundary data is well behaved, the solution should be well behaved for elliptic problems. For parabolic problems, that's not always guaranteed. So you could have an explosion, you could have instabilities in that direction. So the boundary layer, for example, becomes unstable as you continue to march along. Okay? So this is an example of a strictly elliptic problem, well-behaved problem. So this is a steady-state heat convection if you associate phi with T. Okay? So I think that's a problem we're going to take to do the discretization in 1 dimension. That is in 2 dimensions. So in 1 dimension, the equation would simply be d squared T dx squared equal to 0. There is no source, steady. Okay, the equation in 1 dimension will simplify to this. And if you are maintaining, as I said, 2 boundaries that are well bounded, T equal to T0 at one end, T equal to L at the other end, and heat flux is 0, then the solution, you can actually integrate it twice. Analytically, you can solve for it. But we want to do the numerical version of it. Okay? So the temperature profile is going to be well behaved between the limits of this. In fact, I think there is a theorem which says that even for elliptic problems in 2 dimension and 3 dimension, the value that you will find in the interior can never exceed the lowest value that you found on the boundary or the highest value that you found on the boundary, unless we have heat source. Okay. Oh, so this is an example of the marching problem that we have already seen, but there are more generalizations.
So there's no any constraint of applying the finite volume method in any dimension?
There isn't. There isn't. The idea is the same as, this is true for finite difference, finite element, and finite volume. We have seen only for 1 dimension. Okay? In finite difference, I guess I did write down for 2 dimensions. And in finite element, we didn't even do that. But so essentially, you have to take the same basis function, write it one in the x direction, the other one in the y direction, and your domain, instead of being line segments, will become area segments in 2 dimensions. So you'll have triangles or quadrilaterals or whatever. And in 3 dimensions, it will become trapezoids or cubes or cuboids or whatever. But the idea is essentially the same. It's a new concept, but the work requirement becomes tremendous. The bookkeeping, the writing, the assembling the matrix, etc. They can be automated. That's why we have COMSOL and Fluent was so successful in carrying that and implementing it in 3 dimensions. So this is a problem, the marching problem, where you have temperature at T equal to 0 to T equal to T infinity. Okay. And the problem specification is at T equal to 0, you have some function f of x. Okay? And the heat flux is 0. So you're maintaining both boundaries at T0. So initially, depending on the excitation that you have, it will give you a temperature profile. Okay, and then you turn it off, and so you're marching in time, and it should reach the solution of that equilibrium problem or the elliptic problem. Okay, so initially this term is present and it is excited, so you get a non-zero, non-trivial profile. But once you turn that source off, Q off, imagine that this is a fin or a rod. Okay, initially it is generating certain heat, and both ends are maintained at T0. Okay, so when you're solving for that steady state profile, assuming that it is a steady state profile, this term is 0. Okay, so you're solving for d squared phi dx squared equals some Q, some source term. So heat is being generated, but it is being dissipated both ends, removed at both ends, because you're maintaining them at the constant temperature. Okay, So the temperature profile will be something like this. T0 here, T0 there, but some steady state profile at initial condition. That is your initial condition. Then you're turning off the heat. Okay, you're setting this equal to 0. So, but this term is not 0 anymore. Right? So you'll be solving this equation subject to this as your initial condition, this profile as your initial condition, and march in time. And that's what gives you this initial condition. At t equal to 0, this function f of x is your initial profile, okay, which is this profile. And then you're just marching in time, and that gives you the steady state profile eventually. Okay, so much for understanding the difference between an equilibrium problem and an evolutionary problem. Evolution need not always be in time, it could be also in space. But now focusing on the discretization process, what you see here, even without the convective term, because there is no problem in the convective term. That requires us to evaluate the flux, convective flux at the boundaries, and there are no derivatives there, so we can actually evaluate them. The problem is only in terms of evaluating the diffusive flux at the boundaries. Okay, these are evaluated at the control surfaces by using the divergence theorem, right? So we need to approximate that. So we need to come up with a mechanism for calculating what those fluxes are, the diffusive fluxes are at the boundary. Question? So it's a formal development of the method for a one-dimensional steady-state problem, diffusion. Okay, we are ignoring the convection for a moment. We've done this problem on every finite difference, finite element, now for finite volume. The key for us is to understand how the discretization is done. It's one dimension, so the dimension is along the x direction here. Okay. I'm laying a grid, and I'm labeling these grids as I said in the general three-dimensional case, here is my point, the central point P. Okay, this is my cell. In one dimension, my cell is a line element, line segment. Okay, and so I have cell boundaries. I need to identify where the cell boundaries are. So you call this sometimes a staggered type of a mesh. Okay, so what happens is I'm trying to keep track of the variable phi that I'm solving at these cell centers. So I construct a cell at the cell centers. I have the actual value that I'm interested in solving for. But these are the cell boundaries. It is only across these boundaries I have fluxes. I need to calculate these fluxes. So the labeling that people use would be to call in one dimension the point on the right hand side is east and the point on the left hand side is west. Capital E for the actual point and capital W for the actual point on this side. In two dimension, as I showed you in the earlier one, you'll call it north-south and then top-bottom. Okay? So there are 6 points surrounding a central point that are related by that flux equation. We need to develop what that equation is. And we are focusing only on the diffusive flux in this particular case. Okay? So this is the control volume. Keep that in mind. And the other thing is you will use lowercase e. I think you'll probably see it in the next figure. And the lowercase w for the boundaries, the cell boundaries. Cell boundaries become important because that's where we want to evaluate the fluxes across. So lowercase means it's on the cell boundary. Uppercase means it's a cell center. Okay? And these are the boundary points. Okay, so this will be your last cell, for example, that includes the boundary, but you either know the boundary value or you know the flux at the boundary value. So you can impose either one of them. So the first step is the grid generation. You need to come up with this staggered grid agreement with the corresponding generalizations for 2D and 3D. Okay. The second step would be the discretization itself. Okay. So here we are going to, as I said, define the distances. So delta x is the volume in one dimension, if you like, the length of the length segment. Okay. And the delta x PE, capital P and lowercase e, stands for the distance from the cell center to the right boundary. So you need to keep track of a lot of these metrics or measures for these grid. Okay, and delta x WP would be the distance measured from the cell center to the boundary. So the boundaries are done with the lowercase e and w. And the uppercase e and w are the next cell centers. Okay, so this distance delta x with the subscript capital PE would be the distance between the nodes from one cell center to the other cell center. So the extension to 2D or 3D is straightforward. Okay, we're going to use the same concept. Okay. Do you understand? Are there any questions? Why do we need to do that? Because our development is based on a control volume. So this is the control volume from west to east. The control volume has a center. In the three-dimensional case, you can call it as a centroid of that, which you can calculate. So that's step one, generating the grid. The step two would be the discretization. Okay? So the discretization depends on changing the control volume to the surface and evaluating the fluxes on the surface, on the east face and on the west face of this quantity. Okay, so let's make sure that we understand what's happening. So the source term we are writing by this. So what does it mean? What assumptions have I made? Have I made any errors? Have I introduced any errors? Source is a volumetric source, right? So if I can calculate the average volumetric source and multiply it by delta V, I'm going to get the total. So in fact, the way that I define this S bar, which is the average volumetric source per unit volume, would be S bar is equal to integral of S dV divided by integral of dV. Okay, but integral of dV is delta V. So S bar, take this to the left side, multiplied by delta V is equal to integral of S dV. Okay, so really there is no numerical approximation involved in that, but it requires a knowledge of how the source is distributed inside your control volume. Okay, and you need to evaluate by a quadrature. So you might use a quadrature formula to calculate if it is not truly constant inside the control volume. Okay, so the real problem comes only in evaluating this flux. Okay, so can you kind of decipher, can you understand how this term became these two terms? It's an integral over the control volume. In this particular case, the control volume is simply a line, right? So I need to find out what is the flux entering through this or the flux leaving through that, right? So you can write this dV as dx dy dz, right? So the dx and the dx you can cancel, so you have integral of dy dz. So that gives you the area perpendicular to that face, the area of the face, right? So that's how you can, and remember this is a flux, so many kilomoles per meter square, or so many kilojoules per meter square, etc. Okay, so that gets multiplied. So tau times this is your flux that gets multiplied by the area. The face area evaluated on the face E and on the face W. Right? So that's how we deal with the flux term, but the problem is how do I calculate this gradient across that? Can you come up with an idea? What would you do if you're stuck at that point? You are, think of you as a pretend curve in the 1960s and 70s, was developing this method, came up to the stage and say, okay, what can I do? What is the best I can do to evaluate the flux? So that the flux is evaluated in a consistent fashion. Okay, what does that mean? if I go back to the previous figure, I am faced now with the problem of calculating the flux on this boundary, on the right boundary, and on the left boundary. Right? So I can say, well, if I know phi at P and phi at E, those are the only things that I am tracking. Okay? These are the discretized versions of the phi. So I know what phi P is. I mean, these are the unknowns, but I'm tracking those at the nodal values, right? So how would you calculate the flux at E if you know these two? One way would be to simply say phi E minus phi P divided by delta XPE, that number, right? What is this? It's an approximation for the first derivative. So there is a numerical error introduced by that, right? But when we say that we must do this consistently, what we are saying is we must use the same formula when you are calculating the flux from this phase to the next phase, as well as the same formula when you're calculating the flux for this next cell. Because the flux crossing that boundary must be the same for both the cells, for the left cell and for the right cell. Okay? And that way you can replace that by these finite difference approximations, and there are variations on that. You can. This is one proposal, and it would become a central difference if the point E is right in between capital P and capital E. Right? And that's exactly what he does. Okay, there you see it. Okay, multiplied by the diffusivity evaluated on that surface. So if diffusivity for some reason changes, with thermoconductivity it could change with temperature, for example, then this has to be evaluated on the phase boundary, on the control surfaces of your control volume. So AE is the surface area. Okay. So this is for the east phase and this is for the west phase. Okay. That's what introduces a numerical error, because you have approximated a derivative, but you've done it in a consistent fashion. So it is still conservative. It will conserve. No matter how big or how small your control volume is, you should find that when you calculate the net flux over all the control volumes, that must equal the difference between what you put in and what you take out. Okay? So suppose you have a pipe and maybe it branches. I think God cannot love this problem, right? You're dealing with these branches all the time, right? So you divide this into a number of grid elements on the surface too. Okay. A method like this should give you, in principle, a perfect balance between what goes in and what goes out. If you evaluate the flux on this surface and evaluate it on this surface and on that surface, they should be perfectly balanced, because we are balancing the fluxes at every interface between the control volume in a consistent way. Okay? But that doesn't mean that the solution is accurate when you compare it with the analytical solution, if there is one. The reason for that is the truncation error has been introduced in evaluating the fluxes across. Okay. And the linearization of the source term. So the source term we wrote as S bar, the average multiplied by delta V. If the source is nonlinear function of phi, okay, then you do basically a Newton type of a linearization, which takes that nonlinear function and writes it as SU plus SP at the point. So your central point is the reference point around which you are linearizing it, multiplied by phi t. Why would I want to do that? Why can't I just leave the source term as simply, this is the source term, right? We are rewriting that source term into two coefficients. One is SU, the other one is SP. Okay. Why are we doing that? If we don't do that, what are the consequences? The other option is simply to leave it as S bar delta V. If I do that, what would be the consequence? What am I going to get when I develop all these equations? I'm going to get a system of algebraic equations in the nodal values, phi E, phi P, phi W, etc. Right? So when I arrange that in the matrix form, where does this go? Goes to the right hand side. Right? So if the right hand side is a large number, it can create problem in terms of the matrix property. So it's a mechanism to kind of stabilize or make the equations diagonally dominant, the matrix diagonally dominant. So you take this coefficient, and because we have phi p, it will contribute to these two parts. So when you see this arranged in a matrix form, you will see what is the impact of linearizing the source term. So here it is. Okay. So here is the source term linearized version of the source term. These are what is happening on the east and west face, and that is your equation that relates the 3 points. The point in the current control volume, what happens on the west face and what happens on the east face. This is the constant part of the linearized source term. So if this is source term is 0, then there's no problem. Set those coefficients to 0, you get the matrix. But if it is dominant, if the source term is dominant, then this term is the one that goes on the diagonal. Right? If you arrange it in a matrix form, east and west is going to go to the top and the bottom. Okay, but this is the term that will go into the diagonal. So that will make the diagonal term well behaved. And in Fluent, I think you have the ability to define these linearized coefficients. So that is how your final equation is going to look like. Now, if you had 2 dimension, this equation will look exactly like this. Phi p equals some coefficient phi w plus some coefficient phi e plus some coefficient phi north, phi south, etc. Instead of 2 terms, we'll have 4 terms. In 3D, we'll have 6 terms. Same idea that is carried through, but all these coefficients you can figure out once and for all and save them. So that is the essential idea behind control volume method, or the discretization process. You express them in an integral form and in a conservative form, okay, so that the fluxes are conserved across phases, and you have to approximate the diffusive flux, the derivative, in a consistent fashion using the values at the nodal points. So you have some sort of a staggered grid, and you're looking at a cell boundary and evaluating fluxes there, but actually tracking the quantities at the cell center. I think there is probably a solution of equations. This is for a very specific example. Okay, heat conduction in a rod with 100 degrees at one end, 500 degrees at another end. So you're essentially showing how to set up the problem for this particular differential equation. The same ideas that we have seen. Okay? But now we have numbers for all of them, because we have numbers for the total length, etc. And so he can show you what the actual matrix looks like. Matrix form of the equation. You can look at the details, it's on the web. So these are the coefficients, and that's how the matrix looks like. It is tridiagonal, just like the finite difference method. And is it the same as the finite difference method? If you use central difference approximation with flux derivatives, in fact, you will get the very similar, it's the same structure. You get the same equations. So there is one paper that looked at in a more generic fashion. For specific examples, you can show that they are exactly the same. The discretized version is exactly the same matrix. You make the right choices. You have to make all the grid points uniformly spaced, etc., and carry out this development, and you will get the same matrix from finite difference or finite element or finite volume. But each one has its own ability to generalize the problem so that you can get different matrices and hence more accurate solutions for different kinds of problems. So if you want to learn more about the finite element method, the book that I pointed out last lecture by Heinrich, Intermediate Finite Element Method, goes through in detail like this for 1D, 1D transient, 2D, 2D transient, etc. And this book does the same thing for finite volume method. So very easy to learn on your own once you understand what the concept is. The starting point is kind of different for each method, okay, but then the path is fairly straightforward. Okay, are there any topics that you would like me to cover in the next last lecture? Just talk about in general? How about you guys? Is there anything that you came to this course hoping to learn that you haven't learned yet? We cannot do full justice in one course, but yeah, let's see what those guys are saying. Simple algorithm for pressure velocity systems. Okay. I think it is important. I was going to do that because that's the key for solving the challenge we need to understand in solving the pressure velocity coupling, and how does finite element method handle and how does finite volume method handle. I think it is important to know. So okay, that's a good suggestion. I'll put that up and we'll see how far we can go in developing the concept of these. Okay, so you guys are okay for middle of, I think maybe we should discuss this offline by email to fix up the date for your presentation and the oral exam. Okay, so I will send the email to you guys the next few days. All right, so we'll have our last lecture on Wednesday. Okay, any questions from here? You guys are all doing well?
For the finite volume, we will always get this type of tri-diagonal systems?
For one-dimensional case. For one-dimensional case.
But
For two-dimensional case,
sparse matrices.
yeah, the tri-diagonal system is also kind of a sparse matrix, right? Sparse matrix simply says that there are lots of many zeros, right? But in two-dimensional case, you will end up with what you will call a block tri-diagonal structure. So it will be tri-diagonal in each block. So along each direction, you will get one such matrix that are arranged. So you will have one block on the top and one block on the bottom below the diagonal, and they will all have diagonal elements. And you need to do this once on a piece of paper. You do it for finite difference, you will understand. The same thing applies for finite element and finite volume. Okay, so see you on Wednesday.
Can you please collect this form and either fill it now?
Yeah, there is a course evaluation